Good day, viewers. This is 300 Plus Academy, where all we do is exams tutoring, ensuring that you ace your next and every exam. Still on the business of Neco 2024, talking about chemistry practical. This time around, we'll be looking at volumetric analysis. Now, the volumetric analysis for this year is one between sulfuric acid dilute H2SO4 and sodium thiazocarbonate 4. But of course, whenever we talk sodium thiazocarbonate 4, in the course of a titration analysis or what we call volumetric analysis, the sodium thiazocarbonate 4 can be in so many forms. We can have it in form of anhydrous sodium carbonate. We can have it in form of the hydrated form, but this time they just put SH2O here. We can have it in form of S2CO3.10H2O. We can have it, just in about so many form, and based on that, that is why we have to look at the various arrays and ways in which the question can come. We may be told to calculate water of crystallization, or may be told to calculate S. It is sodium thiazocarbonate 4, and therefore we must look at the different forms in which we can have the question. So this is going to be a titration between sulfuric acid and sodium carbonate. We are going to pipette the sodium carbonate into a conical flask, and then methyl orange is going to be our indicator here. The moment we add methyl orange into the pipetted sodium carbonate solution in the conical flask, the color is going to change to yellow, and then we titrate or run our dilute H2SO4, which is inside the buret, until a point is reached where the yellow color changes to pink. At that point, we immediately, lock the jet of the buret, and of course take our readings on the buret. So the color change here is yellow to pink. And also take note of the fact that sodium carbonate exists in so many forms. We can have it as sodium carbonate. We can have it talking about water of crystallization. The water of crystallization may not be disclosed. Sometimes the water of crystallization may be disclosed, while certain elements here, are not disclosed. We may be told to calculate percentage purity. We may be talking of, calculating, quite a number of things. So that is why we have to be careful whenever we have sodium thiazocarbonate 4. So having performed this experiment, for this exam in the lab, what we have is very quite direct. This is how our table looks like. Buret reading in cm cube. The units in cm cube covers for all of the buret readings in the table. Okay, final buret reading. So which means initially our buret reading is at 0.00. Then when we run our acid, we find out at 21. Let's say this is our 21 mark. At 21.10, we notice the color change, and then we took the buret reading. So that's the final buret reading. Now volume of acid used is going to be the final buret reading minus the initial buret reading. So 21.10 minus 0.00, we got 21.10. Then we filled up the acid into the buret again, so that is at the 0 mark. And this time around, okay, these are rough. Now this time around we got 20.50, and starting the next, let's say this is our 20.50. So starting for the second titration, we started from 20.50 and we ended at 41.10. At that point, 41.10 minus the 20.50 where we had stopped before. And that gave us 20.60, and then we filled up again to the 0 mark, and we got 20.50. So from this table, we were able to calculate the average titer value, or what we call VA, average volume of the acid used. Since the figures we got here for the volume of acid used looks consistent or concordant, so we can look for the average of all of this, and the average gives us 20.53 cm3. So in the course of this series, the VA we are going to be using, that's the titer value we are going to be using, is going to be 20.53 cm3. At your respective center, you are to use the titer value or the endpoint of your instructor there. So this is just going to be a guide into you knowing how to go about your calculation in the course of this exam. And so what should our question exactly look like? Now look at this question prototype. It says A is a solution of 0.069 mole per dm cube H2SO4. B is a solution containing 8.1 gram of sodium carbonate SH2O in 500 cm cube solution. That is what I'm saying. Our base here, our B, is actually this form of sodium carbonate. Here we were given the concentration of the acid. That's our standard solution. In the case of this, we were given a sort of mass concentration, but we cannot really get the mole concentration that way. But let's look at the question. It says put A into the buret and titrate it against 20 or 25 cm cube portion of B using methyl orange as indicator. Repeat the titration to obtain consistent titers. Tabulate your readings. Calculate the average volume of acid used. That we have done. We have said the average volume of our acid used in the course of all this calculation will be 20.53 cm cube. Of course, we've dealt with that part of the question. We were then given an equation. The equation for the reaction involved in the titration is H2SO4 plus Na2CO3 dot SH2O. We had sodium sulfate. So basically from here, you can see that the number of moles of your acid is 1, and the number of moles of your B is also 1. So that's more like 1:1. Okay. And in the question, it says from your results and the information provided, calculate the concentration of B in mole per dm cube. So we are looking for CB in mole per dm cube now. In mole per dm cube, CB in mole per dm cube, where we already have our CA. Recall that we were given the concentration of the acid to be the concentration of our acid as 0.069 mole per dm cube. Of course, this is our VA, this is our NA. We can see that this is our NB, but our VB in this case, our VB is going to be 25 cm cube, which is that of the pipette. So someone will tell me, is it not possible for me to have looked for the concentration in mole per dm cube here? I wouldn't have been able to look for the concentration in mole per dm cube. Recall that concentration in mole per dm cube is actually concentration in gram per dm cube divided by the molecular mass. Now, I cannot get the molecular mass because fine, Na2CO3 is 106, but this X, I don't know what it represents. H2 is 18, so X times 18, 18X. So that way I will not be able to, even if I can get my concentration in gram per dm cube from the figure I was given here, 8.1 gram in 500 cm cube solution. The fact that I don't know the molar mass means that I cannot calculate the concentration of B in mole per dm cube using the figure here. So this here is the standard solution. So I'll come here and I'll be saying CA VA over CB VB equals to NA over NB. In this case, my CA is 0.069 times 20.53. That's the average volume of acid use. CB here is what I am looking for, times VB is 25 equals to 1/1. From the equation given, it is 1:1. So my CB here will mean 0.069 times 20.53 divided by 25. In this case, our CB is 0.057 mole per dm cube. Okay, so that way we've been able to answer the first question. The second question says we should calculate concentration of B in gram per dm cube. Okay, this is Roman figure 1. Roman figure 2. Roman figure 2 wants us to calculate concentration of B in gram per dm cube. Concentration of B in gram per dm cube here is going to be, since I now know the concentration in mole per dm cube, is going to be the concentration in mole per dm cube times the molar mass. In this case, 0.057 times 106. Your Na2CO3 is 106 here. So what I'm going to have is 0.057 times 106. I'm going to get 6.00 gram per dm cube. That is what my answer is going to be. Now, Roman figure 3, I was told to look for the value of x. I was told to look for value of x in Na2CO3.xH2O. Now, this here, I want to know what my x is. Now, this is about estimating water of crystallization. This is about estimating water of crystallization, and then there is a formula we used for that. We're going to say molar mass of anhydrous divided by molar mass of hydrated, concentration in gram per dm cube of anhydrous divided by concentration in gram per dm cube of the hydrated form. Look at it very well. So we were told to estimate the water of crystallization here. X, what is X here? So how we do that is we say molar mass of the anhydrous. Anhydrous here means the dry form of the compound, and that here is 106. Na2CO3 is 106 divided by the molar mass of the hydrated. The hydrated here is 106 plus 18x. So that's 106 plus 18x, all equals to concentration of the anhydrous in gram per dm cube. That here is 6. Now, concentration in gram per dm cube of the hydrated here, you know, what we calculate here is for the anhydrous. Now, concentration in gram per dm cube of the hydrated, we go back to what we were given in the question. It says 8.1 gram in 500 cm cube. So, in this case, concentration in gram per dm cube of the hydrated is actually going to be the mass that we have divided by the volume in dm cube, and that will mean 8.1 divided by this, we have 500 cm cube. For us to convert this to dm cube, we would have to divide by 1000, and invariably what that will mean is 8.1 times 1000 divided by 500. That will give us 16.2 gram per dm cube. This 16.2 here is the mass concentration of the hydrated. So we're going to slot that in here. So in a bit to solve this, you know, when we cross multiply, this will come here, becomes 106 times 16.2. You know, this will move here. This is going to be divided by 6 equals to 106 plus 18x. When we compute from our calculator, this here is going to give us 286.2. Then this 106 moves to this side, minus 106 equals to 18x, so that way 18x equals to 180.2. So x equals to 180.2 divided by 18. That way our x here is going to be 10, approximately 10. So what that means is that for question C, as you can see in that question, our x there is actually 10. Number of water of crystallization there is 10. Next up, we were told to calculate the volume of carbon dioxide gas evolved. So for Roman figure 4, we were told to calculate the volume of CO2 formed. Now this is just more of stoichiometry. If you look at it very well, this is more of stoichiometry. Now, looking at everything that we've had, for the case of the acid, I can actually convert this to mole, because 1 mole of H2SO4 is stoichiometrically equivalent to 1 mole of carbon dioxide. I'll work out the volume of carbon dioxide using H2SO4, and based on questions I've been asked, I'm also going to work out the volume of carbon dioxide using sodium carbonate, and you're going to see that we're going to get the same answer. So based on this, 1 mole of H2SO4 is stoichiometrically equivalent to, from a balanced equation, 1 mole of carbon dioxide. Now the implication of that here is that, what is the mole of this H2SO4 here? Normally, concentration equals to number of moles divided by volume. So volume in dm cube, mind you. So since here, the way we've dealt with this is that number of mole will then be concentration. Number of mole will then be concentration times volume, but the volume will be in dm cube. So the number of mole of H2SO4 here is actually going to be, concentration is 0.069 times, now the volume of the acid that we use is 20.53, but because it's in cm cube, I have to convert it to dm cube. So I have to divide by 1000. Once I do this, the number of moles of H2SO4 is going to be 0.0014 mole. Now the implication of that is that since 1 mole of H2SO4 is equivalent to 1 mole of carbon dioxide, it means that H2SO4 is 1 mole from a balanced equation. Carbon dioxide is also 1 mole. It means that the number of mole of carbon dioxide is also 0.0014 mole. Now, since I am looking for volume, you recall that mole equals to volume over molar volume. Invariably, what I'm going to have here is that when I'm looking for volume, volume will be mole times molar volume. That's molar volume. So this will mean 0.0014 times 22.4 dm cube. If we compute this, that's going to give me 0.031 dm cube. So here, that is the volume of carbon dioxide from, this is just about stoichiometry. In case you are not convinced about this, let me also calculate the volume of carbon dioxide using sodium carbonate SH2O. So now we can also, just like we've been able to get the volume of carbon dioxide using our sulfuric acid, we can also get the volume of carbon dioxide using sodium carbonate SH2O. Recall that the concentration of B is 0.057 mole per dm cube. What that means is that when we were dealing with B, the volume of our pipette VB was 25.0 cm cube. In the case of the acid, we use 20.53, and that's exactly what we use there. So what this means is that number of moles of B is actually concentration times volume. And in this case, the concentration is 0.057 times the volume is 25. But in a bit to convert it to dm cube, that will be divided by 1000. So in this case, when we compute this, we would also get 0.0014 mole. Compare it. Number of moles of B is 0.014. Number of moles of H2SO4 is also 0.0014 mole. Take note, this is 1, this is 1. So the number of moles will be the same. This is also 1. So the number of moles will be the same. So the implication of that is, if you say 1 mole of Na2CO3.XH2O is stoichiometrically equivalent to 1 mole of CO2. 1 over 1 equals to 0.0014 mole divided by mole of CO2, and therefore mole of CO2 will be 0.0014 mole. Now, the volume of CO2 in this case is going to be mole times molar volume, and that will still be 0.0014 times 22.4 dm cube, and that will still give us exactly the same thing we got as 0.031 dm cube. So that way you see that either you are using H2SO4 or you're using carbon dioxide. Some will insist that because you're calculating carbon dioxide, the carbon dioxide is coming only from sodium carbonate, therefore you cannot use this. No, you are saying that because you don't have a good knowledge of stoichiometry. When you have a good knowledge of how stoichiometry works, you will know that you can calculate carbon dioxide from this, and even from this, if we know the mole of sodium sulfate. That is how things work in chemistry. It is stoichiometry we call it. So that ends question 4. So to question 5, as you can see on your screen, it says, what is the volume of A? That's the volume of the acid that will liberate 1.12 dm cube of carbon dioxide. What that means is that, what is the volume of A that will liberate or produce 1.12 dm cube of carbon dioxide? So this is just like a door we need to open, and we already have a key, because if you look at it, 20.53 cm cube of the acid of A had actually liberated 0.031 dm cube. See, 20.53 cm cube of the acid was able to liberate 0.031 dm cube. So if we cross multiply this, if we equate this, what we have is that VA times 0.031 equals to 20.53 times 1.12. So volume of the acid that will liberate 1.12 dm cube of carbon dioxide is going to be, if we compute from our calculator, you can see this is going to come here, this times this, and then this moves here. So this is going to come as the divisor. So if we compute this from our calculator, so this will give us 741.7 cm cube. Yes, 741.7 cm cube. That is the volume. Look at it, 20.53 cm cube liberated 0.031, not even up to 1. So if I am having to liberate 1.12 up to 1, then you should know that the volume of acid A that would have liberated that would have been much. So that is why it is 741.7 cm cube. And that ends that question. This is a question prototype. Recall that we are dealing sodium carbonate here, and when we deal sodium carbonate, anything is possible. And with that, we've come to the end of this lecture talking about volumetric analysis for Neco 2024 chemistry practical. From myself and the entire team, it's bye for now.